Alright, in this video we are going to talk briefly about MOSFETs, which stands for, bear with me, metal oxide semiconductor field effect transistors. So if you thought BJT or bipolar junction transistor was a mouthful, here you go. We are specifically going to be talking about N-channel enhancement mode. Enhancement, I can spell, great. MOSFETs, again, I mentioned in the BJT video, there are tons of different types of transistors. We are not getting into semiconductor physics at all in this series. We are just going to go over these N-channel enhancement mode MOSFETs because they conceptually work similar to the BJTs we saw in the previous video, where you have some low power control signal coming from something like a microcontroller or an Arduino that you want to send to your transistor, which you are using, I didn't really save myself enough space here, to control current through some higher power load. And when you turn this, your control voltage on, then your load is going to be on, and when your control voltage is off, your load is going to be off. Again, there are other types of transistors where this relationship is reversed. When you turn this voltage off, then the load's going to be on, but we are specifically talking about the NPN BJTs and N-channel enhancement mode MOSFETs because they kind of have this intuitive relationship where, okay, my control signal's on, so my load is on, and vice versa. The MOSFET is going to have 3 pins, like the BJT, but the symbol is a little different and a little more complicated to draw. We kind of got a bunch of little extra lines in here. Going to look like this, and our 3 pins are called the gate G, which is analogous to the base of the BJT, the drain D, which is analogous to the collector of the BJT, and the source S, which is analogous to the emitter of the BJT. So I should probably draw that BJT symbol over here again. If you remember this, we had the base B, the collector, and the emitter. So we're going to see kind of analogous behavior here, where in this case, a voltage applied to the gate is going to control a larger current through the gain to the source. Here we had a current applied to the base, controlled a larger current through the collector, and then we had the emitter current was equal to the base current plus the collector current. The difference here with the MOSFET is that the gate current, I should have drawn that with a capital to be consistent. The gate current is 0. So the MOSFET, if we are ignoring the fact that the gate actually has some capacitance, so that tiny capacitance can charge up a little bit, so there can be a little bit of current while that capacitor charges up. For our purposes, we're just assuming that the gate current is 0 and that this is voltage controlled instead of current controlled. So here remember, I'm not going to go through it here. You can go back and watch the previous video. We had this linear relationship in the active region between the collector current and the base current, and then eventually we would saturate and the collector current would reach some maximum value. Here we are controlling this drain current using the voltage we apply to the gate. So when connected to a microcontroller and a load, like we saw in the previous video for the BJT, the circuit is going to look something like this, where we are going to tie the source to ground. The drain is going to be connected to our load, which then may go up to some higher power supply with a MOSFET. You might see it labeled VDD instead of VCC. So there is our load resistor RL. Now technically we're controlling the gate with a voltage, so we don't need a resistor here to limit the current like we did for the BJT, but for the sake of protecting your microcontroller, you might have one there sometimes where just in case something bad happens to your MOSFET, if this fails short and that resistor wasn't there, then you would be shorting your microcontroller pin to ground. So you might still have a gate resistor RG, even though that isn't going to factor into the equations that determine your drain current. Now for the operating regions for the MOSFET, this is a little more annoying because the terminology for it can vary depending on which textbook or website you look at. So we have the triode or linear or ohmic region, again, depending on where you look. So this is where it is just beginning to conduct. or acts like a variable resistor, depending on which textbook you look in. And here, I'll put quotes there and parentheses there, whatever. This is once the gate to source voltage, VGS, has started to exceed the gate source threshold voltage. So you'll see this in the MOSFET datasheet. VGS, TH, for this to, TH, for this to start conducting, we need to exceed a threshold voltage there. Again, kind of thinking about what we've seen in previous videos for the behavior of a diode, even though the gate to source junction here is not acting like a diode. Current does not actually flow there, but if you were to plot this, you would kind of see a similar graph where this is, x-axis here is VGS and ID is the drain current. If you start out with 0 and just dial up this input voltage, now remember there's no current through this resistor, so the voltage drop over this resistor is 0, so your gate voltage here is just equal to Vn. You are going to see pretty much zero current through the drain until you hit that gate threshold voltage, at which point your current is going to start going up, VGS TH. So again, in practice, when doing this with a digital microcontroller like an Arduino, where this is either 0 or some higher voltage, then you're not really worried about exactly where you are on this curve. It's either just going to be on or off, but there are equations that can tell you kind of exactly what the current would be given this setup. So in this initial ohmic, linear, triode, whatever you want to call it, region, when it is just beginning to conduct, the drain current is going to be K, which is called the conductance parameter. And that's going to depend on the individual MOSFET. Remember back for the BJT, we had beta, the gain. So here we have something called the conductance parameter, times this big messy equation, 2 times the gate source voltage minus the gate source threshold voltage times VDS, so that's the voltage from the drain to the source, minus 1/2 VDS squared. So I'm actually not going to do an example in this video. I'm just kind of showing you these equations so you know that you could figure out this current given these values if you needed to. But again, in practice, when using an Arduino to control a motor or something, you're going to go buy a MOSFET. You're probably not going to actually bother calculating what the current through your motor should be. So that is one region. And then again, depending on where you look, the next region is either called the active region or the saturation region, which is kind of confusing. If you go look at the Art of Electronics, a very popular electronics textbook, they call this an unfortunate choice of terminology because the saturation region here corresponds to the active region for the BJT. I don't know the history of who made up the terms or why. For example, if you go look on Wikipedia, it then calls this the active region. But anyway, we have a somewhat simpler equation where ID is now just kind of proportional to this difference, well, the square of the difference between the actual gate voltage minus the gate threshold voltage. Sorry, that's a 2 there, without these kind of VDS terms in there. So again, 2 different equations that are kind of going to describe different regions of operation where ID is related to, again, the primary parameter here is this gate threshold voltage, but then you're also going to have a voltage drop over your load, which is going to determine your voltage VDS here. Not going to go through an example in this video like I did for the BJT video because we're just not going to place as heavy of an emphasis on it in this course. The point, or what I want you to remember, is the difference between a MOSFET or FETs in general. Again, field effect means that it is voltage controlled, and whereas BJTs are current controlled. So here we are controlling the current through the base, which then controls the current through the collector. Here we are controlling the voltage at the gate, which then controls the current through the drain. But in either case, you can hook one up to a microcontroller to control a load like this. Now in practice, FETs are a newer technology, so I think if you go read the Art of Electronics, again, they have a little paragraph about the dominance of or differences between FETs and BJTs, and they say something like 90% of transistors in the world today are FETs, but there are still applications where BJTs are superior, so they have not gone away completely. So that goes way beyond the scope of this series and just covering the basic operation of these 2 devices, where again, we only talked about N-channel enhancement mode MOSFETs and NPN BJTs. So if you want to read more about all the different types of transistors, including types I didn't even mention in these videos and the advantages or disadvantages or why you would look at or use one type over another, go check out The Art of Electronics, because I will not make any attempt at claiming that I have anywhere near the level of expertise of the authors of this book.